Hi there, in this video we're going to look at the Laplace transform of the derivative of a function. Okay, so if we look at a function f of t and the Laplace transform gives a function f of s, then what we're interested in is if we've got the derivative of that function, what is the equivalent of in the complex frequency domain of that derivative. Okay, so that's the question there we're wanting to answer. So we'll just write this out. So the Laplace transform of the function f derivative of t is just going to equal the integral from 0 to infinity over function f derivative of t times e to the minus st by dt. Now we're going to use integration by parts to solve this, and I suggest that if you're not sure about integration by parts, you can go to the video on the snippet section that deals with integration by parts, but I'll just quickly go over it. Now the whole idea about integration by parts, if I just write this out, if you had some function, you're integrating say two functions, you call one function u and you call that function dv, then that's equal to u times v minus the integral of v du. Okay, so I've kind of written out in shorthand there, but the whole point about doing integration by parts is that you're able to change the integrand, you're able to change the differential in a function. So for example, this function here is this integral here is a function of u and dv, and then if we miss out this bit here, it then becomes an integral of v du. Okay, so it is equivalent in this instance up here of, instead of having f of t, you're going to end up with, instead of an f derivative of t, you're going to end up with f of t, and instead of having e to the minus st, you're going to end up with the differential of that, so that's going to be minus s e to minus st. Okay, so in effect you're swapping these two round about, okay, and you're making one the derivative and you're making one just back to its original function. Okay, so that's the idea of integration by parts, and I suggest if you're going to learn anything from the calculus, then integration by parts is one of the most useful things to learn. So I'll go over it in kind of longhand, okay, and then after that I'll just quickly show you how you can come to the same result very quickly in your head. Okay, so if I write f derivative of t equals say our dv, and we say our the e to the minus st equals our value u, then we could say that f of t, okay, so in order to get to f of t we'd have to integrate this, so you'd have to integrate that, so you'd end up back with our v, and if we differentiated that, so we got du, then du would be this differentiated, which would be minus se to minus st. Now just plug these into the equation above, and you're just going to end up with u times v, so it's going to be e to the minus st times v, which is f of t. Okay, so that's just the u times the v, and that's from the limits from 0 to infinity, and we're going to take away the integral from 0 to infinity of our function, which is going to be v, which is f of t times du. Now the du is this here, which is minus se to minus st. Okay, and that's all by dt. So this here can then be, I'll write this bit out here again. Okay, so the minus and the minus cancel. Okay, so you're just going to end up with a plus. You have an integral from 0 to infinity. You'll have the function of time here. Okay, now the s can come out of the integral because we're differentiating with respect to time t, not with respect to s. And okay, and s is not a function of t, so we take our s out here, and we're just going to be left with e to the minus st by dt. Okay, so if we then come down again, we can look at that and say, well that there is just equivalent to s times, and this whole thing here is just the Laplace transform of f of t, okay, which is f of s. So it just becomes f of s. Now, what's interesting is this part here. As time tends off to infinity, we know that this thing here, e to the minus st times f of t, we know that limit as t tends to infinity, that must be 0. Okay, we've seen that in previous videos, so it's really the prerequisite for our Laplace transform to exist. So if we want the integral for our Laplace transform, which is f of t times e to the minus st, if we want that to converge, then this thing here must converge as t tends towards infinity. Okay, so it's just really down, and it's down to the fact here that e to the minus st is going to look like that. So it's going to tend towards 0 as t tends to infinity, and assuming that we want to assume that the product of these two terms tends towards 0 as t tends to infinity. Okay, so we know that. Okay, so we know that's going to give us a value of 0. Okay, so we're going to have our 0, and then as this tends towards 0, now it's really this is what's interesting, is what happens when it tends towards 0. So we know that when e to the minus st tends towards 0, this whole thing just tends towards 1. So you're just going to have e to the 0, which is 1, or you could just draw out that function there, okay, which is e to the minus st. Okay, as t tends towards 0, that function e to st tends towards 1. Okay, so it means that we're going to have 1 times, well, it's 1 times the value of this function f of t when t equals 0, which just means it's going to be f of 0. Okay, so we've got these terms here now, so what we're going to have here is minus f of 0. So we could write down here Laplace transform of our function f derivative of t equals s f of s minus f0, and that's the useful and interesting part there, the fact that when we find the Laplace transform of our function in the complex frequency domain, it actually has a factor of just the value of the function, okay, f0, so it's just the actual value of the function f equals 0, which is quite interesting, and it's useful as well, as we'll see just in a minute. Now if we were to look at this, and we could, a lot of the time whenever you're going through this process, and I know the first time I've seen this process, it just looked like it's just all pure maths, and say you think to yourself, well, how do you know to use integration by parts, and how did you know to split the function up like this, and how did you know you would end up with this, blah blah blah. Okay, so one of the ways to look at this is, if you're used to using integration by parts, you could quickly jump down to the bottom line there, because if you look at that there and you say, right, I'm looking to find that integral there, and now the way to solve that integral, now you would know it would be integration by parts, because what you could say is, you could say, well, I don't want, this is complicated, I don't want to be solving it for a derivative time, okay, because I don't know what that function is, it could be anything. So if I could just make it a function of time, and I can pass the derivative on to this here, because I can work out the derivative of this here, so it gives you a starting point to say, well, to work out what this integral is going to be. So I would know, using integration by parts, just straight away I could instantly look at that and say, well, when I do integration by parts, I'm going to have a minus, there's a minus there, and you're still going to have your integral from 0 to infinity, okay, but you're going to have, these are going to be swapped over, so this here is going to just become your f of t, okay, so that becomes your v part, and this thing here then becomes the derivative, so you then you differentiate this section, so if I differentiate that there, you end up with your minus s e to the minus st, okay, by dt, okay, so then you can jump for that line there, you can say minus s, minus and minus cancel out, You can take the s out because it's not a function, so then you can say that's going to be s integral 0 to infinity over f of t e to minus st by dt. And you know that there is s, and you know that there is the Laplace transform f of s. Okay, so you could jump for this line here to that line quite quickly if you're used to using integration by parts. It actually almost looks, well, obviously I've done this quite a few times, okay, and I suppose maybe it's just the more times I do it, the more obvious it tends to look, okay. What's interesting here though isn't that part there. What's interesting is actually the part that's left over here. So you can jump this part quite quick, but it's what's left over here is interesting. And I suppose in your mind's eye, you could jump to that bit reasonably quickly as well, because you're able to then say, well, we know that this we know we're going to end up with this, and this, we know that this here does tend towards 0 as t tends to infinity, because that's how we define the convergence of a Laplace transform, and you are going to be just left with your f of 0. Okay, so it's a wee bit wordy there, but it was just a kind of description of how you can kind of think about these things, so that doesn't look, too, it just looks like I've pulled it right out of the hat. So okay, so now I'll go through a little example here, okay, so that we can, well, first of all, we've done that for the first derivative. We can then do the same thing for the second derivative. So you could say the Laplace transform of f double derivative of t, okay, equals, so what we're doing is we know to find the Laplace transform of this f derivative of t is equivalent to taking s times f of s. Okay, so if we were then to find the Laplace transform of the second derivative, it'd be equivalent to looking at s times Laplace transform of our f derivative of t. Okay, and whenever we find the derivative of this is just going to be f derivative of 0. Okay, so we're just ending up with, in place of this f derivative of t, we're replacing it with the Laplace transform of it, which is just this part of the function here. So you're just going to end up with s times, well, this becomes s f of s minus our f of 0 minus f derivative of 0. So that whole thing then becomes s squared f of s minus f of 0, okay, minus f derivative of 0. Okay, so that's the Laplace transform of f double derivative of t. Okay, so you can have a wee read over that again, convince yourself of that. So what you could do, you can write a kind of general method of doing it, which I'll write down, but you tend not to really know. If you were to take this to the third term, okay, so you'd end up with Laplace transform of the third derivative of t, then what you'd end up with is you'd end up with your s cubed f of s minus s squared f of 0 minus s f derivative of 0 minus f double derivative of 0. Okay, so you can see then that there's a kind of process occurring here. Okay, so what's happening is the s is going down. Okay, so s squared, s, and then s disappears, and as s drops down, okay, the values of the f of 0 start increasing. So it's f of 0, f first derivative, f second derivative. Okay, so you can use that, and what you can do is you could write out, and I'll write it out kind of generally, as I say, you might not need to ever use this because you're tending only to be interested in first, second, maybe third derivatives. But so the Laplace transform of that, we're going to have the nth value of s, so that's s to the n times f of s, and then it's minus all this stuff here. Okay, so all that stuff there, you can call that p of s. Okay, now we know that p of s is going to look like it's going to be the Sn minus 1, because that's the n minus 1th, n is 3, so Sn minus 1 times f of 0 plus Sn minus 2, the f derivative of 0, plus, and if you come all the way along, okay, and at the opposite end, whenever the f start increasing, you're going to end up with a s f of, and that would be n minus 2, say, of 0, and that would be plus f of be n minus 1 of 0. Right, so that whole thing here, this polynomial here in p of s, can then be written out as sum from k equals 1 to n of s of n minus k f of, and that would be k minus 1 of 0. Okay, so that means we've got this thing here would be in place for our p of s, and we would just have, if I put it down in a second page here just to finish it off, so you're going to end up with this value, so fn of t, when I do the Laplace transform of it, is going to be our value Sn f of s minus the sum from k equals 1 to n over s of n minus k times f of our, and that's our k minus 1 of 0. Right, okay, a bit of a mouthful that, and at least you've seen it once, and if you ever see it again, you'll not be scared of it, you'll know what it is. But as I say, you tend not to use it. You just know how to find the Laplace transform of the first, second, and third derivatives, and that pretty much do you. So here's an example here. So the whole point of it, and really the whole idea of the Laplace transform, is to help us to solve differential equations. So if you had, say, f double derivative of t plus 4 times f derivative of t, and again I'm going to go over lots of examples in a separate channel, okay, because this channel really just meant for the mathematics as opposed to the actual practicalities of doing the maths. Okay, so 5f of t equals 5 times u of t, then you can rewrite that as, and it would be this would be s squared f of s minus s f of 0 minus f derivative of 0. Okay, so that'd be the first part of it, and that would be plus 4 times, and that would be s f of s minus f of 0 plus 5, and that would just be a f of t becomes f of s, and that whole thing would just equal, that would be 5, and the Laplace transform of u of t is 1 upon s, 5 upon s. Okay, so the interesting part is the fact that you're given the initial conditions. So if you're given the initial conditions, f of 0 equals 1 and f derivative of 0 equals 2, then you can put these initial conditions back into that equation there. Okay, so you'd end up with your s squared f of s, and that would be minus, so f of 0 is 1, so minus s minus, and f derivative is 2, so it's minus 2 plus 4 s f of s minus 4 plus the final bit 5 f of s would equal 5 upon s. Okay, so that can then be rewritten. So if you rewrite that, you take out your f of s, then you get your s squared plus 4s plus 5. That would equal 5 upon s plus our s, is that s? Yep, plus 6. Right, okay, and then you can take that down, and if you multiply top line, bottom line by s, then you could end up with f of s equals s squared plus 6s plus 5 all upon s, all upon s times s squared plus 4s plus 5. Okay, so then you can do the inverse Laplace transform of that. Okay, and when you do the inverse Laplace transform of that, you get back to the time domain, which is the solution's time domain. That's the whole point of doing that Laplace transform. Okay, this is going on for quite a bit, this video now. I don't think there's anything else I want to say. Okay, thanks for listening, and the next video will go on, we'll start looking at integration. Okay, thank you. Goodbye.